can we start recording, please?
Yeah.
Okay. So let's continue, people. Okay. So this is Q, first moment. This is the sector. If we make a cut, we start the integration on the side. Okay. Now let's go on. We have to be careful because here the variable is S. Okay. This is the dependence. And here, the dependent is on Y. So we go from there up and down on the side. And the deck, it's left, right. Now, after we do this, the next step, remember, is to integrate, to calculate this term integral. This integral helps us to calculate the U. Okay, that's the displacement in the axial direction because of the shear. Okay, so let us remember we have a section here. Okay, and we have something like this. Okay, so what we're going to calculate is this. Okay, this is what we are calculating. Okay, to calculate that, we need to integrate du dy. Okay, so here, please, we go from 0, that's the neutral axis, to y. And you see that this is a function here. It's a function of y. This is something that I have to insist. I think in your class notes, I forgot to include this dependence. Please check. This is a function of y. This is a function of y. Okay? Now, since we're integrating from here in any position, in the vertical position, and then we have to integrate on this side, okay? We need, in order to continue with the integration, we need to know the value of this at the top. That's why we evaluate this at h/2 plus and minus. So we go like this, have the largest value, and then we go on with the next, in the next part, which is the deck. But we go from the neutral axis. So we go like this, and then we turn to the right. Okay, so when we have to integrate on the right, we need the integration, the full integration on the side. That's why we need these two values. You can see here that these are specific values of this function, the integral at the top and at the bottom. Now, we are integrating, let me show here, we are integrating from here until here. So this part here was integrated, see, it's like path 1, and this here is path 2. So the integration from here to here is this. And now we need to evaluate this part here. But for this part here, the Q is different. Okay, and this is the Q. And you see that here, this is B. Remember, when we started, we said, okay, we are going to consider both sides. And that's why we have to consider the thickness equal to twice, the B equal to twice the thickness on each vertical side. Okay. Now, again, this is a function, okay? The result is a function in S. Okay, that means that if we can take this result as function of S, okay, we could calculate the axial deflection. Okay, Okay, if this is S, we could use this integral in order to calculate the axial distortion. See, this is U. And we could use this expression, this integral, to calculate this U of S. Okay? And you see immediately that if you have any point on the deck, the U should be constant because you are at the same position, vertical position from the neutral axis. But because of shear, this U has been changed. And that's the influence of the shear stress. Okay, so this is just function. Now, what's next step? Then let's go back again to number 3. Mr. Pesantes, what's next step after calculating this, the integral of S? What's next step? Mr. Pesantes, what's next step?
It's kind of the correction.
The correction of what?
The correction of the normal stress, because we have an integration, and them multiply EPX over GY. GA.
You're getting, I mean, there is a very simple step. I mean, anybody remembers what's the next step? What's next step? Anybody? The thing is, right now, we can calculate this shear influence on the normal stress. And the problem is that this influence takes us away from equilibrium. So we have to calculate is how much are we away from equilibrium. And this how much we are away from equilibrium is simply delta M. And this is what we have to calculate now, okay? So this is what we have to calculate. And this integration is over the whole section, okay? Over the whole section. It's something that we have to have in mind, okay? First, we integrate in the sector. Then we integrate from the neutral axis up to a certain point. Now we have to calculate over the whole section. Okay, now we have to be careful here because we have two parts, okay? And this is one part, and this is the next one here. Okay, so this is here, and this is from here. Okay, so we have to be careful because in this case, the area, differential area, is simply here. This is the differential area. And this is the differential area. Okay, so you integrate simultaneously on both sides. So you integrate a little bit here and a little bit here. A little bit here plus a little bit here. So you add this plus that, and that's what you have here. 2 times T dy. You add this plus that, and this is what you obtain, 2T ds. You should be able to complete this. This is an integration of polynomials. That's very easy. And this is the final result, okay? Here, again, check units. I'm not going to do it. You have to do it. That's part of your job. You have to check the units, okay? And then now we have all parameters to evaluate, numerically evaluate the new distribution of normal stress, okay? Here we have uniform load. We're going to assume, I think it says in the class notes, This is a simply supported, their uniform load. Okay, it's negative, so it's pointing downward. Okay, so we have something like this. So the deformation will be like this. Okay. Miss Jimenez, the bending moment in this case will be positive or negative? Miss Jimenez. Miss Jimenez.
Yes, I'm right here. It is positive.
Yes, positive. Okay. Because you see that the beam is smiling. Okay. So the upper part will be in compression and the lower part will be in tension. Okay. Here, we are evaluating the bending moment in the central part, the central point of the section. We have already an expression for delta M, and you see that the delta M depends on P. Okay, I forgot to mention here, I'm sorry, in this calculation, I forgot to mention that we integrated only over the half of the section, okay? See, we integrated in the top. And then we simply double. Okay. I'm sorry, I forgot that. Ms. Santos, do you have a question?
Yes, doctor. The last part you integrated over the whole section for the flange beam.
Yeah, because I have a lower flange too. I mean, the top flange, okay, this produces the same result as this one here. So what we do here is simply we integrate this, I'm sorry, this thing here, and we simply double in order to consider this and that. So we consider only the upper part of the section and then we double that.
It's like to do the same for all of the sections.
Exactly. So you integrate from this part, tac, 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 and up to here. It's the same as you integrate from here until here and then double. Because the stresses will be the opposite sign down here, and also the arm will change sign. So that both will contribute to the bending moment.
Thank you, Doctor.
Ms. Santos? Okay. So this is the information. Now, we have this delta M, as I was saying, delta M depends on P. And P here, you see that it is negative, right? That's why delta M is negative. Something which is very important here is the fact that this is the delta M, which is producing an imbalance, right? So, and this divided by that give us 33%. So this is a very important amount, okay? We could calculate that in the previous example. Here. You see here that this is 520. So if this were 625, that would be 10%. So this is about 7 or 8%, okay? 7 or 8%. In this case, the amount is about 33%. So that's a large amount. That tells us that in this case, okay, the shear influence in general, okay, this is just a general comment. It's much more important than in the previous case, okay? So that's something that we should always worry about. Okay, now, this is just an evaluation of the expression that we had before, okay? So remember that we have three expressions, okay? So we have sigma x from pure bending. Then we have sigma x from the correction, from shear. And now we have sigma x because of Taylor for to have balance, okay? So we have to add these three. Now we have to be careful because here, well, we should put a negative here. There. And this depends on delta M. This depends on M. And this depends on the integral of Q dy over B. Okay? So you have an idea. No, I'm sorry. This depends on Q only. Okay. This is what we have here. Okay, so you see that this is the bottom here. So this is bottom. Okay, this is side. This is the deck. And you see that on the bottom, y is minus 3.5. On the deck, y is plus 3.5. Okay. Then we have this. This is the integral. So this is the integral. In some cases, depending on y. In other cases, depending on s. We have to be careful. Okay. Now, this is pure bending. And we said that in the bottom, we will have tension. In the deck, we will have compression. And this is because of pure bending. You see that on the deck, okay, the normal stress is uniform. On the bottom, normal stress again is uniform. On the side, there is a linear variation. This is from the shear, okay? And this is, remember, this is du, dx, okay? And this u is the integral of du dy in dy, okay? And this is the result. And this is the correction. This is proportional to delta M. Okay, delta M is the amount of bending moment that we know that it is in balance. So we have to subtract that in order to recuperate the exact amount of bending moment in this section. And finally, we add the three quantities. So it's the column 4 plus column 5 minus column 6. And this is the result. Okay. And we see immediately that, I'm sorry, this is the value of S is taken so that we can evaluate over the deck. But we only evaluate half of the section because we know that it is symmetric. Okay. You see that this is at the center line. Okay. And this is the connection between side and bottom. Okay, here, this is the connection between side and deck. And this is, again, center line. Okay, and we see immediately that this number, this value here, is 263. And this value is 231. So in the connection between the side and the bottom, okay, the normal stress is much higher than the the value at the center line. And that's because of the shear, okay? The shear acts in a certain direction on the side, and then you have to change direction because you have, on the bottom, you have the bottom plate, okay? That change in direction causes a shear lag, which increases the normal stress in the connection between these two elements, okay? Similarly, in the connection between the side and the deck, okay? And this is the drawing, okay? Sorry, we are missing the name of the variables here. So this is the S, okay? This is measured from center line at bottom, okay? And this is sigma X in general, okay? So this is center line at bottom. This is center, this is bottom at side, neutral axis. This is side at deck, and this is center line at deck. Okay, and as I said before, okay, you see that there is an increment in normal stress. Originally was this, and now we have this. And this is higher than the value at the central position. Okay, so if you draw, okay, you draw normal stress, you're gonna have on the bottom, you're gonna have tension. Okay, you're gonna have something like this. You reduce like that up to here. Okay, and here you have the average value, which is the value from the pure bending theory. Okay, similarly on the top. On the top, you have higher stress on the connection and lower at the central part. This is what you see here. Okay, so you have compressive there. This is the average. And on the connection between the vertical side and the deck, the normal stress is a little bit higher than on the central line. Okay. Questions, people, questions?
Yes, doctor.
Questions? Yeah.
I had a question. Carranza.
Yeah, go on. Okay.
For the shed, the bending moment using in the table in the previous part is using the Simpson rule.
Yeah.
My question is consider the separate bottom, side, and deck. The Simpson rules and summation the part and multiply 2 or consider total summation.
I don't have the class notes. Let me see if I have the class notes. Okay, you're talking about the table on page. Oh, okay, okay. You have to do that. Okay. So let me erase a little bit here. And let me erase all of this. Okay. We have to remember that this is for one side only, okay? That's something which is very important. Okay, now. So we have to recognize that this is from the bottom. This is from the deck. Okay, so what we have to do here is we have to have a Simpson factor, and then here we have the product. We have to be careful here because the product is equal to Simpson factor, which is this, times sigma corrected, and we have to multiply by y, which is this one here. Okay, now you repeat this calculation or copy the same formula in this column. And then what I do is I integrate from here to here. So I multiply this delta S by 3 twice, okay, because I need to consider both sides, okay? And then multiply by the summation. Here, I add these results, and I say this is delta Y divided by 3 twice, because we have two sides, multiplied by the. And this, again, it should be, the result should be the same as this one. It's going to be twice delta S over 3 times this summation. So this is summation 1, this is summation 2, and this is summation 3. So this is 1, this is 2, and this is 3. We have to be careful because we have to integrate by parts in every region. And for every region, we have different spacing between the points of evaluation. Mr. Carranza?
Doctor, in the products, it's considered multiply minus.
No. Okay, yeah. At the end, yes, you're right. You're right, because okay, the formula is minus normal stress times, and I'm missing something here. And anybody, there is an error here in these formulations to get the moment. What are we missing in this formulation? Anybody? What are we missing? What's wrong in these formulations? I made a mistake, I recognize, but you have to try to see what's wrong with these formulations. What's missing? Let me ask somebody. Mr. Nieto, what do you think? What are we missing here? What are we missing? Can you check the units, Mr. Nieto? Can you check the units of these summations, of these, I'm sorry, these expressions?
I don't know, doctor.
No? Mr. Gomez, can you help us?
No, doctor.
No? Mr. Ortega?
Yes, doctor, the minus sign, the sigma correction.
Okay, yeah, okay, minus sign, that, but that's something else. That somebody said that. Mr. Carranza said that. We're missing some. What are the units of these terms? Each one of these terms. Okay, what are the units of these terms? What are the units of this? What are the units of this? We're multiplying sigma and times y. So the result of this, how much is this? What are the units of this product? Mis Puertas, what are the result of the, what are the units of multiplying these two terms? Mis Puertas? Mis Puertas.
Teacher.
What are the units of sigma, Mis Puertas? No. You should have this in your memory, Mr. Dylan something, Mr. Vanegas, I think. Mr. Vanegas, what are the units of sigma? Mr. Vanegas. Mr. Vanegas, wake up. Isaac, please. Isaac, please.
Okay, good.
What are units of sigma times y, Mr. Carranza?
Or over length.
Yes, force over length. And if you multiply by delta, the result of the delta S, the result will be delta S times force over length will give you, Carranza, will give you,
for length.
no. You
Only-
said correctly
force.
that this
Only force.
force,
Only for.
but we need what units? We need force and length because we are calculating moment. What are we missing here?
Length.
What are we missing? What? The thickness, people, the thickness we're missing because this is sigma dA, okay? So we're missing the thickness. So this has to be multiplied by, here, I'm going to put it, and finally here. Yeah, we need a negative sign as somebody said. So you add these three terms and you should get something similar to the value that we had originally. Questions? Any questions about this, people?
Doctor, I'm Paredes. I have a question.
Yeah.
For example, that figure is symmetric. What about if the figure is not symmetric on the neutral axis? We integrate, for example, from the top to neutral axis, and after that, neutral axis to bottom.
You have to be careful, simple as that. I mean, for example, let's suppose just that we have, for example, typically the thickness at the bottom is different than the thickness at the top. Usually at the bottom, we use higher thicknesses, okay? So that's the case that you're mentioning, right? And in that case, what we have to do is we have to integrate by parts. In the real world, usually, for example, the thickness on the side is not uniform, all right? So what we have to do is simply we integrate in every region, okay? So, okay, let's suppose that we have, by some reason, okay, we have T side 2 and T side 1. Okay, so in this case, it's like having 4 regions, deck, bottom, side 1, side 2. But what you have to do is you integrate in every region. In that case, the thickness will be constant. Or something else that you can do is you get here in the multiplication, you could also do multiply here the Simpson factor sigma y, and also include here the thickness, right? And you have to consider the thickness according to the position on the side. Paredes?
Yes, doctor, thank you.
Okay, no problem. Yeah, the only difference is that in that case you have to be careful, and the integration will take more. I mean, we could not take advantage of the symmetry anymore. We have to be careful with that. That's all. Of course, the position of the neutral axis will not be at h/2 in that case, right? So we have to be careful with the regions. Okay, is there any other question, people? No? Okay. Now, assignment 3, I just posted yesterday. There are 2 problems. Okay. Oops, sorry. Let's go from the bottom. Mr. Kimi, Elvis Kimi, can you read it, please, Mr. Kimi?
Good morning, doctor. Yes.
Go on, read it.
About the assessment number 3,
Assignment, Mr. Kimi.
assignment number
Assignment. Try to pronounce the
Assignment.
last letter. There is a T there, right? I would like to listen to that. Assignment. Go on.
assignment.
Okay, go on.
You are asked to analyze the influence of shear force on the normal stress distribution of the tube with rectangular section, which was analyzed as an example in class.
Okay,
Consider
so yeah, just a second. So this is the example that we analyze in class. So this is the case that you have to analyze. Okay. The problem, as I said before, is that if we consider the simply supported case, I don't think we have done the example in class. It's fine, but I think we need to make it a little bit more realistic, and that I will explain that in a minute. Okay, so it's the same rectangular section, but in a different situation. I will explain that. Go on, please, Mr. Who was reading? Mr. Kimi, go on.
Consider the barge is simple support.
Simply supported.
Simply supported on both ends. And the load is uniform with a value of
whatever.
40.
Okay, minus. Okay.
Minus 40,000 kilograms over meters. Calculate.
Meters, yeah. Please, when you read, you see that there is a point here, right? So you have to pronounce, so you tell the audience that you're finishing one sentence, okay?
Okay, doctor.
A value of minus 40K kilograms per meter. You see, they are finishing the sentence. Go on.
Calculate and plot on the position X
Position. The first
position
is S. Position. Go on. At
position
echo. That's fine. Great.
X
equal
L or for the following.
Okay, so this is what you have to calculate and plot. First, go on.
Shear stress distribution.
Distribution.
Number 2, normal.
Distribute. The U here is pronounced IU. Distribution. Go on. Second,
normal stress distribution. Considering the shear distortion of the section.
Okay, this is what I want you to calculate. And the third,
axial section distortion of the section.
Oh, there is it's double. It says axial distortion of the section. Okay, so this is U. Okay, that's the axial function of every point in the section. So we are supposed to have a absolutely straight section if we accept kinematic assumption. But since we include shear, that shear will take us away from that. Okay, so we are not going to end up with a flat with a linear, I'm sorry, a straight section anymore. Okay, so you're going to have like this, and then it's going to deform. How much? That's what you want to calculate. Okay. Thank you, Mr. Kimi. Mr. Hidro, if you have to calculate the shear stress distribution, what would you do? I mean, remind us of what you need to calculate the shear stress distribution, Mr. Hidro.
the inertia, the Q, and the time.
Following you. I'm sorry, we have problems with your microphone.
Hello.
Yeah, go on.
I remember that the inertia, the first, the section.
Do you
Q.
remember the formula? Do you remember the formula to calculate the shear stress? Do you remember the formula? It's V times
Q over I.
Over I and
The
I
thickness.
and B. Yes. What is Q? What is Q?
Q, the first moment of area.
Exactly. So it's equal to what? How do we calculate easily?
The integral of y and the differential of area.
Yes, yes. So that's good. So that's first thing. Miss Jurado. Tell us something about point two, normal stress distribution. Anything that you remember to calculate the point two, Miss Jurado.
Yes, doctor.
Do you remember anything about solving the point two of this problem? The normal stress distribution considering the shear distortion? What do you have to calculate to complete this assignment? Point two.
First, the shear stress and the inertia too.
Okay, the inertia, that's something that we know. Tell me something I don't know. That's the example that we have completed today, right?
Yeah,
What was the first thing that we did?
We need to consider the problem is symmetry. So we need to integrate just.
Come on. Give me something that useful to me. Miss Arechua, give me something interesting here. Huh? How do we calculate the normal stress distribution?
We must
Considering the shear
calculate the normal stress plus the correction.
Yeah, okay, we have to calculate delta M. To calculate delta M, what do we need?
Delta.
Delta M.
A ver. We need
We need a
we
lot.
calculate the inertia, we calculate the
And that's
Q.
something we know. That's,
Yeah.
inertia is something that you calculate in solid mechanics. This is a more advanced class. Miss Flores, tell me something about how to complete the part to this.
And we have to integrate the BQ divided by the B.
Okay.
And
so for this, we need Q. Okay.
yes.
What else do we need to complete this?
We know the values from E, the value from G and Y.
Don't such information. Come on. What next step?
To calculate delta M.
Can you help us, Ms. Santos? Next step.
Our first was first moment, and then integral.
We have that. Come on.
The integral of
the integral of what?
Q over B.
Then what?
Then have the delta moment of Taylor.
Yeah, and now we have three terms, right? Do you remember the three terms, Mr. Aizaga? Do you remember the three terms that we have to combine in order to complete part two? Describe. The first one.
Is the shear stress. No. Sorry. The normal stress.
The what?
No,
yeah,
sorry.
This is normal stress. But the first term, tell me something about this first term. Let me go somebody else. Let me go somebody else. Ms. Poveda, tell me something. What's the first term? That's the easiest one, Ms. Poveda. What do we have here? No?
Sorry,
Mr. Ramirez?
Doctor, I can't hear you very well.
Yes, I'm asking you to tell me if you remember what's the first term that we need in order to calculate the normal stress distribution considering the shear influence. What's the first term here? Oh? Oh, okay, Mr. Vasquez, do you remember the first term?
It
Mr.
is
Vasquez.
minus m over.
And what would you call, how do you call that? What's the origin of that term? No?
Is for the u of s.
No, you said minus my over what?
I sub c.
I sub c. And how do you call this term? I mean, from where do you get this? Mr. Zurita, you remember?
Normal.
From where do we get this? Mr. Zurita, from where do we get this? I'm sorry?
The normal stress minus m multiply y over inertia.
Yeah, but from where, I mean, how do you call this term? Anybody? Mr. Santos, Ms. Santos, how do you call this?
Pure flexion.
Pure bending.
Pure bending.
This is what you learn in solid mechanics. The second one is the correction. Yes. So the second one is the correction because we consider here, okay, in the second one, we have the differential with respect to x of u, and u is the integral of du dy, okay? And this is the function, the integral y. This is what we need this. And the third one comes from Taylor. Okay. Ms. Avilés, do you remember the last term? How do we evaluate this last term? Do you remember?
And yes, doctor, I remember that term. And is minus and delta n over inertia times y.
Yeah, but this needs a minus up here.
Yes.
Yeah, remember, you have to subtracting that, and that is also a negative. So we have to be careful. I have said this many times. I'll be honest. You have to be careful because we have a negative, a negative, a negative. You are young enough, you can remember, but you have to be careful. Okay? So that's the general idea of that. Now, for this axial section distortion, okay, this is something that we mentioned here. Okay, so for this is we need u in general, and we need to integrate, okay, du, dy, dy. And this is u, this du, dy, it's an approximation of tau divided by g. Okay, because we neglected dv dx. Okay, so that's what you have. And this is this integral that we have here. So you take this integral and you simply evaluate it along the many points of the section, and then you have to draw. Okay, so at the end, for the last part, okay, according to the kinematic hypothesis, we keep this section straight. But with this, it's going to be some distortion. Okay? So this is something that you have to plot. And please don't give me something like this. It has to be something like this. Okay? So we have to do this pure bending, and then we have to add this because of the shear. I hope you put that in your memory. Okay, so in this case, we are considering this situation. Okay, let's assume that this barge is simply supported on both ends, and the load is uniform. Okay, this is P sub 0, and you see that it is negative. Now, how do you describe the shear force distribution on that beam? Let's ask somebody at the end. Miss Leon, how do you describe the shear force distribution, Miss Leon? How do you expect the shear force distribution be in this on this beam? Shear force.
Oh, okay.
Here, on the left will be positive or negative?
Negative.
Yes, negative.
Maybe
And then you see that this P is constant. So we have dV dx is all equal to minus P of x, right? Since this is uniform and negative, minus P of x will be constant and positive, right? So the variation is constant and positive. So more or less, that's going to be the variation. Bending moment. Mr. Sawai, how's going to be the variation, the distribution of bending moment on this beam? What's going to be the bending moment on the end? Mr. Sawai, on the end, bending moment. Mr. Sawai. Mr. Fuertes, what's going to be the bending moment in this end? No, Mr. Dominguez, Salim Dominguez, tell me. Bending moment on the left.
The left is negative, then is positive.
No, bending moment. Here.
Zero. Sorry.
Yes. Why is that?
Because it's simply supported.
Yes. And the bending moment in here, in between, is going to be positive or negative, Mr. Dominguez? That's going to be the deflection, right? So here.
Positive.
Yes, positive. Yes, because it's smiling. Okay, so we were considering, okay, in the example in the class notes, we were considering here, since this is in the class notes, but we see that in this center point, mid-ship section, the shear force is null. So that means that there's going to be no shear stresses, okay? So I want you to calculate about here, L over 4 for this exam, for this assignment. So we're going to have some interesting shear force and some interesting bending moment. Okay, and that's typical when we go to analyze the hull of the ship at the end of the semester. When we want to analyze the bending moment, we go to the midship section. And when we want to consider the shear force, we go to L over 4. okay? So that's why I want you to analyze in here. Is there any question, people, because I'm running out of time? Is there any question? Please, I need you to start right away the homework, the assignment, okay? And for next session, we're going to start a new chapter. So please, I'm going to try to give you a couple of questions about that, okay? Something that you review before the session, okay? Quick read, and that's all, okay? Okay, people, if there are no questions, then I'll see you Thursday. Please start your homework right away. Don't wait until next week. It will be too late, okay? Stay safe. If there are no more questions, then I'll see you Thursday. Bye-bye now.
Thank you, Doc. Bye-bye.
Thank you.
Thank you,
Have a
doctor.
great day.
Sorry for getting too late.
Thank you, doctor.
You're welcome. ¿Cómo vamos?
Todavía se está grabando.
Ok.